So, good morning, students. This is Arvind, Assistant Professor, Department of EEE, DBS IT Kavali. So, in the previous class, I discussed about some three-level converters. Here, I am going to discuss three-level converter operation. So, actually, it consists of two. First is one is operation of three-level converter, and another one is fundamental and harmonic component of the three-level converter. So, firstly, we will discuss operation of the three-level converter and what is the main objective to use the three-level converter in the system, like that. So, firstly, we will see three-level voltage source converter. So, this is the main concept we are choosing. So, three-level voltage source converter. So, here the three-level converter is one which is used to vary the magnitude of AC output voltage without having to change the magnitude of the DC voltage. So the three-level converter is the one which is used to vary the magnitude of AC output voltage without having the change in the magnitude of the DC voltage. So the three-level converter is one concept that can accomplish that to some extent. So here I am taking one phase leg operation. So one phase leg of a three-level converter is shown in the figure. By using that one phase leg, I will explain the operation of three-level converter, three-level voltage source converter. Okay, firstly we will see the diagram. So this is the diagrammatic representation of three-level voltage source converter consisting of one phase leg, not three phase legs, only one phase leg here we are using. So here if you see this diagram, so we have two converters. So and each converter is divided into two halves. So in one half we have one thyristor and one diode, so namely 1 and 1 dash, and so in the second half we have two components, one thyristor, one diode, that is in parallel connection. So these names are 1A and 1 dash A. And coming to the second converter, it is also divided into two halves. So first half consists of thyristor and diode combination. So those are namely 4A dash and 4 dash A. And next in the second half we have two components. So here also they named as 4 and 4 dash, and each halve in both converters, each halve consists of two diodes, namely D1 and D4, and we are taking the capacitor in the two halves. So two capacitors we are choosing, and these two connected to the neutral connection of the diagram. So here we have the positive voltage plus Vd by 2 and the negative voltage is minus Vd by 2, and on the that is on the DC side. And coming to the AC side, that is the converters are connected to the AC side, that is IA. Okay, this is for one phase leg. Okay, next, so the other two phase legs are not shown here. So would be there would be these would be connected across the same DC bus bars. Okay, and the clamping diodes connected to the same midpoint N. So D1 and D4 are the clamping diodes. D1 and D4 are connected to the midpoint N of the DC capacitor. So that is, those are called as clamping diodes, D1 and D4. And it is seen that each half of the phase leg is split into two series connected valves. So already I discussed this thing. So it is seen that each half of the phase leg. So here we are using one phase leg. So one phase leg consists of two converters. So each converter is divided into two halves. Okay. So that is one dash is split into one dash and one A, one dash A. So I already discussed this one, and the midpoint of the split valve is connected by diodes D1 and D4 to the midpoint N as shown. So this is the explanation for this diagram. So total diagram. Okay. And next, so on the face of it, this may be seem like doubling the number of valves from 2 to 4 per phase leg. So actually one phase leg we are using two valves, but here we are using 4 valves per phase leg. So in addition to providing two extra diode valves, that is D1 and D4, two extra dioding valves also we are using. So however, doubling the number of valves with the same voltage rating. So in this case we are doubling the number of valves, that means there is no change in the voltage rating. Okay, so would double the DC voltage and hence the power capacity of the converter. So here we are not changing the voltage rating, but we are doubling the DC voltage and hence the power capacity of the converter. Okay, thus only the addition of the diode clamping valves, that is D1 and D4 per phase leg, that is in the figure A, adds to the converter cost. So whenever we add these two clamping diodes to the phase leg, so it is an additional equipment, so it is added to the converter cost. It is added to converter cost. Next, so if the converter is a high voltage converter, so if we take one converter, so if we think that the converter is a high voltage converter with devices in series, then the number of main devices would be about the same. Okay, the number of main devices would be about the same whenever we take the converter as a high voltage converter with device in series. At that time, the number of main devices would be about the same. And here we are using a clamping diodes. So a diode clamp at the midpoint may also help ensure a more decisive voltage sharing between the two valve halves. So here we are dividing the two converters into four valves. Okay, so here we are using the clamping diodes D1 and D4. So whenever and these diodes are connected to midpoint N. Okay, so these are help to ensure a more decisive voltage sharing. So these are used to give a decisive voltage sharing between the two valve halves. Okay, so on the other hand, requirement that a converter continues safe operation with one failed device in a string of series connected devices. Suppose we actually we are using two converters with four halves. So for example, if we take the one converter continues safe operation with one failed device. So in total connection, one device is a failure, one device occurs failure. That means the converter operation continues safely with one failed device in a string of series connected devices may require some extra devices. May require some extra devices. So here I am taking the output voltage corresponding to one 3-level phase leg. So here we are using one phase leg. That's why I am taking output voltage waveforms according to that. Okay, here we have totally four waveforms. First waveform is VA and second waveform is also VA and next one is VB and last one is VA minus VB. So these are the output voltage corresponding to one phase leg corresponding to the 3-level voltage source converter. So I will explain these things. So coming to the first waveform. So if you observe the first waveform shown is a full 180 degrees square wave. So first waveform is a full 180 degrees sine square wave. Okay, so when we get these waveform means uh, square wave obtained by closing of devices 1 and 1A. So already we seen that the connection diagram of a 3-level voltage source converter with one phase leg. So based on the diagram, the connection based on the connections, so here the first waveform shown is a full 180 degrees square wave obtained by the closing of devices 1 and 1A to give plus Vd by 2 for 180 degrees and the closing of valves 4 and 4A for another 180 degrees to give minus Vd by 2 for 180 degrees. So plus Vd by 2 minus Vd by 2. So I already shown the voltage value in the connection diagram also. So positive voltage is plus Vd by 2, negative voltage is minus Vd by 2. Okay, so 1 and 1A devices closing means we have plus Vd by 2 for 180 degrees and whenever we close the 4 and 4A valves for 180 degrees, it will give minus Vd by 2 for that 180 degrees. Okay, next now consider the second voltage waveform, that is second one, so in which the upper device 1 is turned off. So actually in the previous first diagram we are taking 1 and 1A, 4 and 4A, these four are the upper half of the phase leg. So here in this one, now consider the second voltage waveform in figure B in which the upper device 1 is turned off and device 4A is turned on. So in this case, only one device is on at a time on the upper half. Okay, so here device 1 is turned off and device 4A is turned on at an angle alpha. At an angle alpha earlier than they were due in the 180-degree square wave operation. Okay, so if you see the diagram, you will understand. So this one. Okay, in this case at a time only one device will on. So here one is on means one is in half. Okay, so next, so this leaves only device 1A and 4A on. So this leaves only device 1A and 4A on, which in combination with diodes D1 and D2 clamp the phase voltage VA to 0. So actually, so I already said that in the second waveform we are using only one device turned on. So this leaves only device 1A and 4A on in both the cases, and positive and negative 1A and 4A on, which in combination with diodes, that is the clamping diodes, clamp the phase voltage VA to 0 with respect to the DC midpoint N, that is the midpoint N. So two capacitors connected to midpoint N. So here with respect to the DC midpoint N, regardless of which way the current is flowing. So that will show on the second waveform. Okay, and next this continues for a period of 2 alpha. So actually we started with the period alpha, and this continues for a period of 2 alpha until device 1A is turned off. So actually 1A and 4A is on, but here it will continue for a period of 2 alpha, from alpha to 2 alpha, until device 1A is turned off and device 4 is turned on, and the voltage jumps to minus Vd by 2 with both the lower devices 4 and 4A turned on. So already 4 is turned on, and after that the voltage jumped to minus Vd by 2 with both the lower devices 4 and 4A is turned on and both the upper devices 1 and 1A turned off. So in this case, in the second waveform, we will have 4 and 4A turned on and 1 and 1A is turned off, and so on. Like this the operation continues. Next, of course, angle alpha is variable. So already I said that. So actually the waveform, second waveform starts with the period alpha and it continues to 2 alpha and it also continues and so on. So of course angle alpha is variable and the output voltage VA is made up of sigma is equal to 180 degrees minus 2 alpha square waves. So sigma is equal to 180 degrees minus 2 alpha square waves. And this variable period sigma per half cycle potentially allows the voltage VA to be independently variable with potentially a fast response. So actually here the sigma is a variable period for half cycle, not a full cycle, one half cycle, and it potentially allows the voltage VA to be independently variable with potentially a fast response. So it is seen that devices 1A and 4A are turned on for 180 degrees during each cycle. Okay, so devices 1 and 4 are turned on for a sigma is equal to 180 minus 2 alpha degrees during each cycle. Okay, so while diodes D1 and D4 conduct, these two are the clamping diodes. While diodes D1 and D4 conduct for 2 alpha is equal to 180 sigma each cycle. So like this the operation continues. Okay, next, so the converter is referred to as 3-level. So already I said that it is a 3-level converter, that is the 3-level voltage source converter. So that's why the converter is referred to as 3-level, because the DC voltage has 3 levels. One is minus Vd by 2 and another one is 0 and third one is plus Vd by 2. 3 voltage levels. The converter is referred to as 3-level because the DC voltage has 3 levels: minus Vd by 2, 0, plus Vd by 2. 3 levels we have. Next, as explained earlier, these phase legs can handle the current flow in any phase relationship. So he already said this point in the previously. So the phase legs can handle the current flow in any phase relationship. So turn off devices handle any instantaneous inverter action, turn off devices, thyristors, IGBT, IGCT, like that. The turn off devices handle any instantaneous inverter action, and their parallel diodes handle any instantaneous rectifier action. So in the diagram we have each converter consists of two halves. Okay, so each hall consists of one turn off device and one diode. The diode is a parallel connection to the turn off device. So here the turn off device handle inverter action and parallel diodes handle rectifier action. So clamping diodes D1 or D4 along with the lower devices 1A and 4A carry the current during clamping periods, with D1 and D1 to 1A carrying the negative current, that is current going into the AC bus, that is a negative current, and D4 and 4A carrying the positive current, D4 to 4A carrying the positive current, that is current going into the DC side, D4 to 4A carrying the positive current. And also, as explained before, for the two level phase legs, these three level phase legs can also be connected in different configurations to obtain the required converter. So we have to use the different configurations by three level phase leg by using three level phase legs, and these are connected in the different configurations to obtain the required converter. So these configurations include a single phase full wave converter with two legs. So that is the first concept in this chapter, and a three phase bridge converter with three legs, and star connected secondaries with floating neutral or delta connected secondaries, etc. That is the second concept we deal in this um, chapter. And figure B also shows the output voltage of the second phase VB and the phase to phase voltage VAB for a three phase converter. So this diagram actually in the three phase full wave converter bridge operation. So that the diagram also shows the output voltage of the second phase VB and the phase to phase voltage VAB for a three phase converter. Okay. Next, as discussed previously, the triplen harmonics will not pass through to the primaries with floating neutral. Okay, etc. Two 6 pulse converters can provide a 12 pulse converter. So actually, I discussed this 12 pulse operation in the three level converter also. Sorry, three phase full wave converter bridge operation, and in the previous class, that is transformer connections for 12 pulse operation also. So two 6 pulse converters can provide a 12 pulse converter and so on. So with the three level converter, it should be noted that for the duration of zero output voltage, figure 3.8b, the phase lag currents flows in the midpoint of the two capacitors and thus flowing through the DC capacitor. Okay, so this current is mainly of third harmonic and is substantially independent of the converter pulse number. Converter pulse number. And next, another concept for the three level voltage converter is fundamental and harmonic voltages for a three level converter. So, what the three level converter buys is the flexibility. Okay, to rapidly vary the AC voltage or to provide a defined zero voltage notch to eliminate or reduce some specific harmonics. Okay, so however, when considering the harmonics, there is a limitation in exploitation of this flexibility. Okay, so these things will be explained by using this concept fundamental and harmonic voltages for a three level converter. Okay, so taking into account the AC voltage pulse width of duration sigma. So here I am taking the pulse width of duration sigma per half cycle. The magnitudes of fundamental and harmonic components of phase to DC neutral voltage are defined by. So here I am taking phase to DC neutral voltage V is equal to from the Fourier series. That is V is equal to 4 by pi into Vd by 2 into sine sigma by 2 plus sine of omega t plus sigma by 2 minus 1 by 3 sine 3 sigma by 2 plus sine 3 of omega t plus sigma by 2 plus 1 by 5 and so on. So it will give Vn is equal to 4 by pi into Vd by 2 into 1 by n sine n sigma by 2 plus sine n omega t plus sigma by 2, and RMS value is given by Vn is equal to 2 root 2 by pi into Vd by 2 into 1 by 2 sin n sigma by 2, and fundamental RMS voltage is given by V1 is equal, fundamental means V1, okay, 1, fundamental means 1, so that is V1 is equal to 2, substitute n is equal to 1 to the above equation, that is RMS value, it becomes V1 is equal to 2 root 2 by pi into Vd by 2 into 1 by 2 sin sigma by 2. Okay, this is the fundamental RMS voltage for a phase to DC neutral voltage. Okay, next, so which starts from a maximum RMS value of root 2 by pi into Vd at sigma is equal to 180 and reaches to 0 at sigma is equal to 0. Okay, so starts from a maximum RMS value, that is at sigma is equal to 180 degrees and reaches to 0 at sigma is equal to 0 degrees. So if V1 is assumed to be V1 maximum, so that is equal to root 2 by pi into Vd, that is equal to 1 per unit at sigma is equal to 180. Okay, so the figure 3.9 shows the value of fundamental voltage V1 as per unit of V1 maximum and function of the pulse width sigma. So as seen, the fundamental is 1 per unit at sigma is equal to 180 and decreases with decreasing pulse width, decreasing to 0 at sigma is equal to 0 degrees. Okay, and the figure also shows the values of harmonics. I will show this diagram later. It consists of total harmonics. So from sigma is equal to 0 to sigma is equal to 180, we have one diagram. So I will show later. Okay. So the diagram also shows the values of harmonics as per unit of the actual fundamental voltage VB as a function of the pulse width sigma. Okay. Next, harmonic values as per unit of V1 maximum can be more useful if the purpose is to consider harmonics in terms of the specified distortion levels. So here we have specific distortion levels. That's why here I am taking harmonics values as per units. That to V1 maximum. Actually, I said that previously V1 is assumed as V1 maximum. So V1 maximum is equal to root 2 by pi into Vd, that is equal to 1 per unit I taken. So here it consists of specific distortion levels. So such values can be obtained by multiplying a harmonic level in figure 3.9 by corresponding per unit fundamental level. So in the diagram, we are taking this harmonic level by multiplying with some value. So it is interesting to note the variation in per unit harmonics will with decrease in sigma. So if you see, if you observe the diagram 3.9, so the variation in per unit harmonics with decrease in sigma. So whenever the sigma value is decreases means variation in per unit harmonics, that is increasing 2 alpha, that is equal to 180 minus sigma. This is the value, that is increase in the alpha value. So that is 180 minus sigma. And next, so it is seen that the fifth, seventh harmonics are at their maximum 0.2 per unit and 0.143 per unit respectively at sigma is equal to 180, and then decrease and increase according to the equation above. Okay, so a particular harmonic reaches 0 when 180 minus sigma is equal to 180 by n. At that time the harmonic reaches to 0 where n is the harmonic number. Okay, so for fifth harmonics, this occurs at sigma is equal to 144 degrees and again at 72 degrees. Alage, the seventh harmonic is 0 when sigma is equal to 154.3 degrees and 102.9 degrees and 77 degrees. After the first 0, each harmonic rises again, reaching a peak at 180 degrees minus sigma is equal to 2 into 180 by n. So these peaks are higher than the first peaks because the values shown are per unit of the actual declining magnitude of the fundamental voltage V1. Okay. Next, all harmonics eventually approach 1 per unit at sigma is equal to 0 when the fundamental approaches 0. So it is noted that for operation with a 154 degrees to 144 degrees, both the fifth and seventh harmonics are very low, and the converter almost behaves like a 12 pulse converter. So for operation sigma is equal to 144 degrees, the fundamental voltage also drops to 0.95 per unit, which in effect represents 5% loss of total capacity. Okay, so this is the diagram I am discussing like this. So here this is the fundamental and harmonic voltages for a 3-level converter. So it consists of sigma is equal to 0 to sigma is equal to 180, and sigma is equal to 180 to sigma is equal to 0 degrees, from 0 to 180 and 180 to 0. So here the curve shows that V1 by V1 maximum. So these are the per unit values. On the vertical side we have 0 0.2, 0 0.4, 0 0.6, 0 0.8, 1. These are the per unit fundamental harmonic voltages. Okay, so these are the order of the harmonic. So 5, 7, 9, 11, 13, 15, 17, 19, 21. So like this the values are changes. Okay, and next, as an alternative, it may be preferred to normally operate a 3-level converter at about 154 degrees. So which is where the fourth harmonic is 0 and the fifth harmonic is about half of its maximum value. Okay, in any case, it is a matter of compromising flexibility of voltage control, reduction of specific harmonics, and some loss of usable capacity. So in many applications, it is not necessary to vary the AC voltage independently of the DC voltage, in which case a 3-level converter would be a good way to reduce low order harmonics or to eliminate a specific harmonic. Okay. So alternately, one can normally operate the 3-level converter with varying sigma. So here we are varying the sigma value over a range from sigma is equal to 180 degrees down to sigma is equal to 90 degrees, 180 degrees to 90 degrees, down to 90 degrees, giving a variable AC voltage from 100% to 70%. So it also points to the consideration of a combination of higher pulse converter, DC bus voltage control, and use of 3-level phase legs, that is minus Vd by 2, 0 and plus Vd by 2. And unless the 3-step converter is used within a multi-pulse structure, it is useful for only a limited range of independent AC voltage control. Okay. Next, so this is because the percentage harmonics increase rapidly with a decrease in the fundamental output voltage to below about 70%. This is also shown on the figure 3.0, that is the harmonics. So different curves is there. At that time we are taking fundamental harmonic voltages as per unit value 0.2 to 1 per unit. Okay, on the x-axis we are taking sigma value. Sigma is equal to 0 to 180 and 180 to 0. Okay. So with the split of DC capacitor level, it is essential to ensure that the two capacitors are changed to equal voltage, because unequal voltages will generate even harmonics. So capacitor voltage balance is achieved by a control which prolongs or shortens the conduction time of the appropriate devices. Okay. Next, these curves of figure 3.9 also apply to any other configuration that is based on the square wave with pulse width less than 180 degrees. So note that all the triplet harmonics are 0 at sigma is equal to 60 degrees, which corresponds to the phase-to-phase 6 pulse voltage waveform for a 3-phase full wave bridge. So a significant disadvantage of a 3-level converter is that with increasing sigma, an increasing amount of third harmonic flows into the midpoint of the DC capacitor. That is the only disadvantage we have in the 3-level converter. So this current generates a third harmonic voltage across the capacitors. So in order to keep this harmonic voltage within acceptable limits, the size of the DC capacitor has to be increased compared to that of the 2-level converter. Okay. Thank you. So this is the topic I covered: 3-level converter with one phase leg and a fundamental and harmonic voltage for a 3-level converter. Okay. Thank you.